In laws of motion, let's take some example based on the string. First question is, two blocks of the mass 2.9 kg and 1.9 kg are suspended from a rigid support S by two inextensible wires. Inextensible means length of the wire will not change, and each of length 1 meter as shown in the figure. The upper wire has negligible mass and lower wire has uniform mass density of 0.2 kg per meter. The whole system of blocks, wires and support have an upward acceleration of 0.2 meter per second square. The acceleration due to gravity is 9.8 meter per second square. Find the tension at the midpoint of the lower wire and the tension at the midpoint of the upper wire. So as per the question, given data is that there are the two masses 2.9 kg, say this is M1, and 1.9 kg it is M2, and these wires are of 1 meter length each. Upper wire has negligible mass, so its mass is 0, and lower wire has the mass density, that is mass per unit length is 0.2 kg per unit length, that means meter, and total length is 1 meter, so total mass will be 0.2 kilogram. The whole system of the block, wire and support have an upward acceleration of 0.2 meter per second square. So this is the acceleration in the system. And acceleration due to gravity will be always downward. It is g equal to 9.8 meter per second square. So midpoint of the lower wire is say A and midpoint of the upper wire is say B. We have to find the tension at these midpoints. Now to find the tension at the midpoint of the lower wire at point A, we make a free body diagram. This is the point A on which weight of the body is acting, which is 1.9 g, and weight of the half wire from A to lower end, it will be 0.1 g, and tension at point A will be upward, and net system is moving with an acceleration of 0.2 meter per second square. So now we have to write the equation of motion. It is tension T in upward direction minus downward forces, it is 0.1 g minus 1.9 g. So this is the net force, and it will cause the acceleration in the system, and system has the mass of 0.1 of the wire and 1.9 of the body, and into acceleration is 0.2 meter per second square. So tension will be equal to this 0.1 and 1.9, it will be 2g, plus here it is 2 into 0.2. Substituting the value of g, it will be 2 into 9.8 plus 0.4, it is 19.6 plus 0.4, that is equal to 20 Newton. Similarly, in second case, we have to find the tension at the midpoint of the upper wire. So at point B, which is the midpoint of upper wire, first we have to make the free body diagram. There are the forces acting downward, which is weight of the mass body of 1.9 kilogram, also mass of the body of 2.9 kilograms, so its weight is 2.9 g, and also the mass of the lower wire, and upper wire is massless, so it will be 0.2 into g, and tension at the point B is Tb in upward direction, and whole system is moving with an acceleration a equal to 0.2 meter per second square. So writing the equation of motion, it will be Tb minus downward forces, it is 0.2 g minus 2.9 g minus 1.9 g, and it will be equal to total mass, which is 0.2 plus 2.9 plus 1.9, and upward acceleration is 0.2. So we have to solve it. It is Tb minus, on this adding this, it will be 5g, and it will be equal to 5 into this whole gives 5 multiplied by 0.2. So this equal to Tb equal to 5 into 9.8 plus 1, and it is 49 plus 1, that means it is equal to 50 Newton. Hence tension at the midpoint of lower wire is Ta, that is equal to 20 Newton, and tension at the midpoint of our upper wire, which is Tb, and it is equal to 50 Newton. This is the answer. Second question is, two particles of mass m each are tied at the end of a light string of length 2a. The whole system is kept on a frictionless horizontal surface with the string held tight so that each mass is at a distance a from the center P as shown in the figure. Now the midpoint of the string is pulled vertically upward with a small but constant force F. As a result, the particle moves towards each other on the surface. The magnitude of the acceleration when the separation between them becomes 2x each. As shown in the figure, there are the two masses m which are at a distance a from the midpoint P. There is a force F on the midpoint P which carry the point P in upward direction and change the shape of the figure as we have drawn here now. New position of the midpoint is say P dash and P has moved up. The distance between the masses from the point P is still A, but the distance of the midpoint from the masses are say x as given in the question. Force F is acting on P in upward direction and there are tensions in the string which is T. In this situation, suppose angle of the string with the vertical is theta. So we can resolve the tension in two perpendicular component. Component with the angle theta will be in terms of cos, it is T cos theta, and another component will be T sin theta. Similarly, the tension in the other length can be resolved in two perpendicular components and this will be again T sin theta and T cos theta. Therefore, on balancing the force with the downward forces that are the tensions, we will have number one equation that is F equal to T cos theta plus T cos theta that is equal to 2T cos theta. And similarly, we can see here that the force on the mass M is tension and tension is again resolved at mass M in two perpendicular components. Angle with the vertical is theta, so component along the angle will be T cos theta and in horizontal direction it will be T sin theta. And because the particle or the mass particle will accelerate along the x direction, so we'll write T sin theta will be equal to m into a. So from the equation number 1, we can find the tension in the string, it will be F by 2 cos theta. And from equation 2, the acceleration of the mass particle will be equal to T sin theta by m. And we will substitute the value of T, it is T by 2 cos theta into sin theta by m. And it will be equal to F by 2m into tan theta. And from the diagram, we can find the value of tan theta. Here, the value of distance from M to P dash is x and distance between M to P is A. So from the right angle triangle, this PP dash will be equal to square root of A square minus x square. So we can write that tan theta is perpendicular by base. So perpendicular is MP dash and base is PP dash. And substituting the value, we will have F by 2m. MP dash is x and PP dash is root a square minus x square. Hence, option B is the correct option. Third question is a uniform rope of length L and mass m lying on a smooth table is pulled by a constant force F. What is the tension in the rope at a distance L from the end where the force is applied? Suppose on the smooth table, a rope of length capital L is placed and a force is applied at one of the end. We have to find the tension at a point P which is at a distance at small l from the end where force is applied. So distance of the point P from the other end will be capital L minus small l. In this situation, there will be tension at the point P and this tension will be balanced by each other. So tension is on right side is T and there is a tension on the left hand side is T. If we may divide this rope in two parts and make the free body diagram, first part is having the length capital L minus small l. It has a force which is tension on one end and there is no other force on the other end. And other part which has the length small l, there are the two forces. One of the force is F and another force is T. This is the tension. So we write the equation of motions for these parts. In first part, we can write F minus T. This is the net force. This will cause the acceleration. So mass of the part will be total mass by total length. It will give the linear mass density and multiplied with the length of the part which under consideration. So it is L and then acceleration. So this is our equation number 1. Similarly, for other part, we can write there is net force is T. This will be equal to mass, total mass by total length. It is the linear mass density and then the length of the part. This is capital L minus small l and then acceleration A. Because this rope will move with acceleration A, then both part will also move with the acceleration A. This is our equation number 2. So now divide equation number 1 by 2 because we have to find the tension. So we have to eliminate the A, acceleration. It will be F minus T by T. It will be equal to m by L into small l into A divided by m by L into capital L minus small l into A. A and A get cancelled, m by L and m by L get cancelled. So this implies that F minus T by T will be equal to L by capital L minus small l, or we can write it as F by T minus 1 equal to L by capital L minus L. So F by T will be equal to L by capital L minus small l plus 1. Taking the LCM, it is L minus small l and we have L plus capital L minus small l. Small l get cancelled, so it is L by capital L minus small l. Therefore, we have to get the tension by force on inverting. So it will be L minus small l by L and tension will be equal to F into L minus small l by capital L, or also can be written as F into 1 minus small l by capital L. This is the answer.